Okay, so let's go ahead and finish up 10.2 here. We're looking at the nth term test for a divergent series. And so we're going to consider this series. If we look here, this is going to be 2 over 1 plus 3 over 2 plus 4 over 3 plus so on and so forth. This obviously diverges, and it does this because each iteration here is it's growing, and so it's not going to reach. It's going to outgrow basically any kind of any kind of number or any predetermined number, because every little as our sum goes, it's just going to keep growing and growing and growing, and so it's going to diverge. So basically, if we look at this, it says if our sum from n equals 1 to infinity of an converges, then an goes to 0. And keep in mind, try and remember that this means right here, this, basically what this is saying is if an infinite series converges, then this is the limit as n goes to infinity of an equals 0. All right, of our so basically if our series converges, then we're saying if our series converges on our infinite series converges, then our limit to infinity of our sequence will converge to 0, because that kind of makes sense. If the sequence blows up to some big huge number and keeps growing and growing and growing and it doesn't actually drop down to 0, then we're going to always be adding larger and larger numbers on, and so if we start summing all those terms, then it's going to keep growing as well. So the only way that's going to happen is when that limit of the sequence goes to 0. So here we have the nth term test for divergence. Here this says our series from 1 to infinity diverges if the limit of our sequence there fails to exist or is different from 0. All right, so in other words, if this basically ends up being something like anything, 1, 10, 50, infinity does not exist, something, as long as it does not equal 0, then we're in trouble. Or at least we're not in trouble, then it's divergent if it doesn't equal 0. So it's kind of the opposite of the previous one. So let's take a look at some of these. So here we've got the limit, or we've got our series from from n equals 1 to infinity of n squared. And so we can just look at the limit as n goes to infinity of n squared, and that's infinity. And so therefore our series diverges. So pretty simple there. Let's take a look at the next one. We'll take a look at what we're taking the summation of. So let's look at the actual sequence. So limit as n goes to infinity of n plus 1 over n. That's going to equal the limit as n goes to infinity of n divided by n is 1, and plus the just 1 over n part. And that's going to end up being the limit as n goes to infinity. That's a 1 plus a 0. That's a 1. That does not equal 0. Therefore, our sum diverges. Okay? So they diverge because it doesn't go to 0. I mean, if you keep adding up non-zero terms, it's never going to go to 0. Or I guess they can be non-zero, but they have to be getting smaller and smaller, closer to 0. The terms have to be going to 0. All right, so let's take a look here. How about here combining some series? So if we have a series equals A and the series B, so we have these two series, and they are convergent series, then here are some things that will work. One, you can sum them. The sum of all the individual components of the series is also equal to the sum of them separately, which we can just say is A plus B. The same thing with the difference. If we do a sum where we put all the differences together, we can also separate them. And then we can also constant multiply. If we have a constant on every term, then we can actually bring that out front and multiply the whole thing by. So that works for any number k as well. So here are some corollaries, some things that are going to follow because of these because of this theorem up over there, because of these rules we've got. Every non-zero constant multiple of a divergent series diverges. So if you have a series that diverges 2n plus 2 over 2, and we just saw, we can write this as the sum of 2 times n plus 1. Oops, sorry, I meant to have this over n, not a 2. 2 plus n over n. Well, this is 2 times the sum of n plus 1 over n. And on the last page, we saw that this diverges, therefore this whole thing diverges. All right, so therefore this one diverges, the 2n plus 2 over n. All right, if a series an converges and the series bn diverges, then the sum of the two series, or the difference of them, also both diverge. All right, so all it takes is one of them to diverge, because it's going to blow the whole thing up together. The other one's going to go to 0, and so you essentially, as you go to infinity, you're going to have zeros plus something that's growing and diverging, which means you're going to have growing and diverging. You're just adding only one of them's going to 0. And so a quick example of that would be something like 1/2 to the n minus 1 plus the sum of n squared. Notice I'm not writing from n equals 0 to infinity all the time now. It's just a lot of writing, but something like that. This is going to be our sum of 1/2 to the n minus 1 plus n squared. And this is going to diverge. This diverges, again, because this part may go to 0, but this part is going to go to infinity. And so infinity plus 0 is just going to still be infinity. It's still going to blow up. All right, here's something you need to be careful of. If, we only need one if one series diverges and the second series B diverges, it doesn't necessarily mean that their sum diverges, because their sum may still converge. All right, like if one's diverging negative and the other's diverging positive, they may cancel each other out. So be careful with that one. So if this is our sum, this is 1 plus 1 plus 1 plus so on and so forth. And this one here, -1, is -1 minus 1 minus 1 minus 1. Oops, not plus, minus dot dot dot. Well, if we do 1 minus 1, this is the sum. So those were two divergent ones. This is the sum of 0, which is just 0 plus 0 plus 0. And then so that one's converging. So the summation of those two diverging series actually converges. So go ahead and take a look at page 596 and 597 for deleting terms and re-indexing, to see if you can do that. But what I'm going to do is just add a page here real quick, and we'll go ahead and take a look at that. Sorry, it's making noise at me. I'll turn that off. So let's take a look at adding / subtracting terms. This sometimes might be a useful thing to do. So for example, if we have n equals 1 to infinity of 1 over 5 to the n, we could actually make that 1/5 plus 1/25 plus 1 over 125 plus a sum from n equals 4 to infinity of 1 over 5 to the n. Essentially what we took was this part out here, which is the sum from n equals 1 to 3. And so this is our sum from n equals 1 to 3. And so we can have that part on there and kind of pull that out, whatever that number is out of there. So we've taken it outside of it. And then another one we could do is n equals 5 to infinity of 1 over 2 to the n. So on that one above, we were adding. If we add terms to a series, we can get that. This one, We could also do, so we started at n equals 5, we can start at n equals 1 to infinity of 1 over 2 to the n, but then we'd have to remove the n equals 1 to 4. So we'll do minus 1/2, minus 1/4, minus 1/8, minus 1/16. All right, this part right here being our sum from n equals 1 out to 4. Okay, what you need to pay attention to on this is this does not change convergence or divergence. Okay, removing terms from it is not going to really make a big difference there, so it's not going to change that. The last thing we can do, let me add another little page here, is the reindexing. And again, you still need to go into the book and take a look at these two things. But the reindexing, what I mean from that is, say we have the sum from n equals 1 to infinity of of 1 to the n minus 1 over 2 to the n minus 1. This one can be the sum from n equals 1 to infinity of 1/2 to the n minus 1. They both have the same n minus 1 power. Well, what we can do is actually do some different versions of that. You can do something like n equals 0 to infinity and do 1 over 2 to the n, right? You could do n equals 5 to infinity of 1 over 2 to the n minus 5. And you'll notice that if you start at these things, you're going to end up going to the same value. And you could even do something like this, say n equals -4 to infinity of 1 over 2 to the n plus 4. And you'll notice that if you do it the same starting place on each of these, you're going to start off with the same values. So all of these are equivalent. We've just given them different indexes to start. All right, well, that's it for 10.2.